Okay, this is my next video. This time I'm going to try and do a little bit of code, show you what I'm doing in my code, and in addition to that, show you what's going on in in the graphics window there. Um, so, all right. So this is just a plane. It's composed of probably some 200 times 200 vertices, 200 along the length and 200 along the width. And what I want to try to do is a variety of different transformations, vertex displacement transformations, to show how the vertex shader works, and then also to show how the fragment shader can do the lighting and make it look kind of nice using the old school ADS, ambient diffuse and specular lighting system. So I'll start out here in my main function, and I have a light position, so that's controlled by these sliders here. This is along the x-axis, this is along the y-axis, and you can kind of see the light moves where you would expect it to move in the z. So I just apply the model view matrix to the location of my light, and it moves it to where it needs to be in the scene. So the other thing that you see here is this displace vec. So this is my actual displacement of my vertex data. So if I come up here, there's two displacement functions. One is going to be a continuous function that's a function of x and y. So it's a damped oscillation. So I have the damping coefficient is e to the minus ud times x times e to the minus ue times y. So if I come over here to my slider window, I can mess with the amplitude a little bit, and you see this is what I want. You see here, if I pull these way down, ud and ue, I get like your standard sinusoidal wave. Then I have inside of the sinusoidal functions, I have this UB, which controls the frequency, and UC, which controls the phase. So if I mess with UC, you can kind of tell that the phase is getting played with, and if I mess with UB, you can see the oscillations become more frequent. There, turn it way up. So that's sort of that. The idea is that I just pass I just use the vertex, GL vertex, to get the X, and the GL vertex to get the Y, and then the Z, I'm using the X and the Y to compute the location, the Z location of the vertex, and then I'm keeping W the same, and then I'm outputting it. I'm returning this vector here that I've made. I call it V displaced vec, and if I go up to the top, you can see I'm outing V displaced vec, and it's F of GL vertex. It's the function applied to the GL vertex. So the other thing that I do, if I check this box over here in this window, in the configuration window, if I uncheck that box, then you'll see that it's you use polar coordinates. So in this case, I have here, I call displacement vec polar. So displacement vec polar is going to do this business here. I take this is the amplitude, and this is the radius, right? The radius computed the way that you would expect it to be computed, the square root of x squared plus y squared, and this is the dampening function. So as I move further away from 0, r gets larger, which in turn causes this dampening coefficient to get smaller and smaller. So if I turn the amplitude way up, and then I turn UD way up, the dampening pulls everything to 0 along the edges of the square. So here you can kind of tell too, if I increase UB here, I can get larger, more frequent oscillations. Lighting sort of looks right. Looks kind of like lipstick, I think. And then I return the vector that I've computed, and ultimately I out the position without any transformation, so that I can compute the normals later on in the fragment shader, and I out the model view or I coordinate position So that's just the model view matrix applied to the displaced vector. And then I set the position of the current vertex to the model view projection matrix applied to the displaced vector, which is sort of what you would expect, kind of simple. So so that kind of got these are the sort of the big three, and then the light position. Oh, and then the texture coordinates, which later on I'll use to do some noise, to do some stuff with some noise. I out all of this to the fragment shader, and ultimately it's the fragment shader that makes things look pretty. So if I come over here to my fragment shader, I'll scroll down to my main function and sort of start here. So the first thing that I want to do is I want to compute the normal vector. And the normal vector is going to depend on whether or not I'm using x, y coordinates or polar coordinates. And in the case that this is checked, right? In the case that this is checked, I'm using Cartesian xy coordinates. So the normal here is this function displacement normal. So I scroll up to displacement normal. You can kind of see what I'm doing. This is to keep x and y positive. I do this to keep x and y positive. And then here is sort of the nitty gritty. So I'm taking the derivative of this z with respect to x and the derivative of this z with respect to y. So you can kind of see here the math. You got to do some math. Math is healthy, it's good for you, it builds character. So here I've done some math and taken the derivative of the function that I'm back in the vertex shader now, that I had created in my vertex. So I take the derivative of this function with respect to y, the derivative with respect to x, and I get two tangent vectors. If I zoom in kind of close, one tangent vector is going to go kind of like up like this, and another tangent vector is going to go across like that. And I want to find the normal vector, which is going to be the cross product of the two, and it's going to be poking out of the sine wave here, kind of orthogonal, sort of like this guy. This is the normal vector, and normal to it are the two tangent vectors, one that points up the sine wave, one that points across the sine wave. And those are found by taking the derivative with respect to x and the derivative with respect to y. Here we go. So tx, this is the derivative with respect to x. I've set it to 1, 0. So like if you think about this, this is x is 1. This is the x, so this is 1, and then my z is dz dx, which is going to be something in here. It's going to put me somewhere in here. Actually, there we go, somewhere in here. So depending on where it is, it could point kind of up like that, or could, and I'm just, pretend the y axis isn't there, and my cursor is just going along up and down along the z axis. I'm going 1 unit down my x-axis, and I'm going dz dx units up my z-axis. And then in the case of the derivative with respect to y, I'm going 1 unit down my y-axis, and I'm going up dz dy units on my z-axis. And this gets me, you can kind of remember this white line, this x-axis line here. This is the, you can imagine that's the normal, right? dz dy is getting me the vector that goes across, and dz dx is getting me the vector that kind of points up the sine function. So to get the normal vector, this is normalized, like make it the length 1, but to get the normal vector, I take the cross product of tx and ty. Once that's returned, I normalize it, so that means that I make the length 1. And you probably remember that the length of a vector is the square root of the squares of its components. So for example, if a vector is an x, y, and z component, its length is the square root of x squared plus y squared plus z squared. To normalize it, I divide each component by the square root of the square of the sums of its components. Boop. It's kind of a lot of math there, but it's healthy, it's good. So math is good. So if I come down here to my main function again, the other case, when I uncheck this box, is the polar coordinates. So I pass in this v position, by the way, by the way. This is good. So V position is just GL vertex. It's the non-displaced vector. So I'm passing the non-displaced vector to compute the normal in the fragment shader. So if I come up here, let's see, displaced normal. Yeah, so if I come up here to displacement normal, polar. So in this case, I'm doing something very similar, but instead of taking the derivative of z with respect to x, I take the I still take the derivative of z with respect to x, but r, the radius, is actually a function of x. So there's a little bit more math, and you can use the chain rule in calculus to compute the derivative with respect to x by first computing the derivative with respect to r, and then everywhere that you have a dr dx, you do you take dz dr. So everywhere you have a dz dr, you'll end up also taking the dr dx, and you get something like this. So this is the derivative of this function, x over r. The derivative of this function right here with respect to x is x over the square root of x squared plus y squared. And then the rest of it is here. So I guess the only difference here is that I'm taking first the derivative with respect to r and then applying the train rule to get the derivative of r with respect to x and the derivative of r with respect to y. So then I do the same thing. I compute my my tangent vectors. You know, one, this is sort of like the normal vector here, and it's got two tangent vectors, one that points up and one that points across, and then I cross those two to get the vector that's normal and normalize them and return it. And that ultimately gives me my displaced normal. Ta-da! And so from there, I can sort of start doing my lighting. So the first thing that I need is the point from the vector from point to light. So this is the point, the I coordinates position, minus the light position. I'm sorry, I just did that backwards. The light position minus the I coordinates position. So the point to the light. This is the point, and I'm going to the light. Point to the light. And if you remember, when you take the difference of two vectors, you're sort of completing the man, what do you call that shape? It's not a rhombus. It's not a trapezoid. Maybe it is a rhombus. Well, anyway, it's a parallelogram. You're completing the parallelogram, right? When you take the difference of two vectors. So if I do that, then normalize it, I get the vector from the point to the light. And then I get the point to the eye, and I call that VE, and that's from the point, the I coordinates position, to the eye, which, because I'm using this I coordinates and not not world coordinates, my eye is still at 0, 0, 0. It's still at the origin, right? And then I get the vector from the point to the light reflected about the normal, right? So that's reflecting it about the normal. I'm like waving my hand as if you can see it, but obviously you can't see my hand. So this is the VL is from the point to the light, and this is my displaced normal. So I'm reflecting VL across my normal vector. So you can, maybe you know what that means. Hopefully, if you don't, you can Google it, and it's pretty clear. And then here I'm reflecting the point to the eye about the normal. And this negative here ended up being important. I can't remember why right now, but it is important. So first I set the fragment. So this is the fragment shader, remember, that I'm in now. Don't try to do all of this in your vertex shader, or your normal won't be interpolated correctly by the rasterizer and you'll have issues. You need to do all of this in your fragment shader to make it look smooth. So I set first the frag color to the back color, which I've got here, a little function for, or a little button for that. And then I set the frag color to the I use ADS lighting to compute what the frag color should actually be. So if I come up here to ADS lighting, I can sort of explain that. So it takes the normal light to the eye. What was VE again? Point to the eye. Actually, this is a point to the light. VL. Point to the light is VL. Bn is the normal, Ve is point to the eye. This is the reflectant across, these are the two vectors that I reflected across the normal vector. So here I compute the ambient. So this is like, no matter what the normal or any of this is, the ambient is always going to be the same. And you can see that reflected here. If I turn down UK at the diffuse and the specular, you can kind of see the ambient. It doesn't, no matter where I'm looking at it from or what these things are, what my function is here, it's always the same. So it's not affected by the normal, or the VL, or the VE, or the VR, and none of those. It's affected by none of them. So the diffuse is one that is affected. It's affected by the point to the light and the normal vector. The inner product gives you the cosine of the angle between these two. And remember, I normalized them so I don't have to worry about their magnitude. So the cosine of the angle between these two vectors gives you kind of like, you can think of it as the percent of the diffuse lighting that is shining at that fragment. So that's the product of that, the cosine of that angle, the UKD, this is the coefficient I'm setting here, and the current frag color. So if I turn up, you definitely can tell it's doing something interesting. It's changing the diffuse lighting at every fragment in the scene. Then I compute the specular. So first I set specular to 0, and I only set specular if the angle between the point to the light and, I want to get this right, from the point to the light and from the point to the eye. If the angle from the point to the light and the point to the eye is greater than 0, right? So the angle, the cosine of the angle, there we go. The cosine of the angle is greater than 0, right? So think about what values of theta can cosine? What is it like? Cosine of 0 is 1, right? And as I go about my circle, unit circle, I increase theta. Theta goes to pi over 2, and all of a sudden cosine is 0. Cosine of theta, cosine of 0 or cosine of pi over 2 is 0. So when the vector points up on the unit circle, I have no x component of my vector, so the cosine of the angle is 0. And then I continue to rotate my vector around the unit circle, and I start getting negative x values for the cosine of the angle. So you start to notice, okay, so what values is this going to work for? This is going to work for angles between negative pi over 2 and pi over 2. For angles between negative pi over 2 and pi over 2, the angle between these two is going to be greater than 0. And then here I compute the specular component. So if that's true, if the angle between the point to the light and the point to the eye is greater than 0, then the specular is going to be the inner product of the point to the eye and this angle, the angle of reflection. That's what this VR is called, the angle of reflection. So like the idea is, I'll show you in practice what it does. So if I turn up the shininess here and then I kind of make it look shiny, you can tell as I come down here, this like white outline is getting longer and longer. As I come up here, see here, so what it's doing is it's depending upon the angle of reflection. So the percentage of the fragment color that gets set when this percentage of the specular lighting that I show is the cosine of the angle between the point in the eye and the reflection angle of reflection, or the vector of reflection there, to the power of U shininess. So as I increase U shininess, cosine of theta is bounded above by 1. So as this number gets larger, I'm sending the cosine of I'm sending this value here to 0, right? Because I'm increasing the power, right? Boop, boop, boop. So eventually, you can tell as it gets smaller, I get more white. The lines get larger as it gets larger, and if I go in between 0 and 1, you kind of see some interesting effect. It's like the opposite. It's the opposite, because now my power is a fraction, and that's 1 over, so it's the like root, the 0.1829, or one, what is this? What is this? 1 over x equals 0.829, so 1 over 0.829, what is that? Let's see here. 1 divided by 0.1829, oops, 1 divided by 0.11 divided by, oh, I'm in programmer for assembly. Oopsie, I need to go. This is kind of fun. 1 divided by 0.1829. I thought that was going to be oh, anyway, it's something like the 5th root. So it's the 5th root of the cosine function. So between 0 and 1, let's think about what the square root function does. The square root function increases quite rapidly between 0 and 1. So if my U shininess is between 0 and 1, then I'm taking the root of the cosine of the angle, and it's a big number all of a sudden. It's a larger number. As it gets between 1 and infinity, it gets smaller, and then these white specular highlights get smaller and smaller. As I go between 0 and 1, specular highlights get larger and larger. That's the key point. And then I take times UKS, which is this value here, and then I take that times the specular color, which I set at this button here, and then I return it and clamp it to between 0 and 1. Clamp the values between 0 and 1. Okay, so finally, kind of some cool things. So one good way to debug when you're doing this is to set the color of your fragments to the normal, so that you can tell it's changing as you change like the amplitude of the thing, or the that's weird. I'm not sure what's happening there. Oh, that's UKA. I'm so sorry. UA. As I change the amplitude, you can kind of tell that the normals are changing. And the reason why that is because I'm setting the color. So this is kind of a nice trick. Don't forget to set the alpha to 1 though, because it won't work if you don't. So finally, the last cool thing to show you is the noisy. So if I turn off this guy here, I have this very metallic kind of metallic material here. Now, if I change, I want to decrease the frequency a little bit here. There we go. So it's kind of neat. It's kind of like a metallic kind of material. So if I check this noisy box, I can do some cool stuff. So I've got my normal vector that I've computed up here, and the idea is that I'm going to use random numbers to perturb my normal a little bit, so that it reflects a different amount of light, or it reflects light in a different way at every fragment in the scene. So if I come up here to my perturb normal function, I have a noise. So if I come up here, boop, 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 I have my uniform sampler 3D noise. So it's sort of, the idea is that this is a little bit like a texture. It's a noise texture, and I'm using a noise texture to perturb my normal slightly. So if I come up here, you can see it kind of looks like a hammered metal material as I perturb my normals more and more, but it's perturbed in a coherent way, so that, you know, close to a point it's moving just a little bit, but further away it's very random. You can't really predict where the normal is gonna point. Close to, you know, in a small ball around every vertex, the normal's only being perturbed a little bit. But as you grow the radius of the ball around a vertex, the normals of all those vertices around that vertex, their normals are getting perturbed a lot. That's the idea of noise. So as I come up here, mess with this guy, and then I can turn up the frequency of the noise and get kind of like a, you know, man, I don't even know what I would call this material. It's kind of cool looking though. You know, it's It's a little bit odd. Anyways, so yeah, that's sort of what I wanted to show you. So I'm perturbing the angle, and you kind of see here the code. Let me scroll this way so you can see what I'm doing. I'm using the displaced vec here, multiplying it by the U noise frequency, right? Noise 3. This is accessing texture to get NVY, and then I'm subtracting 2 so that the values are between 0 and 1, and then I'm multiplying with the angle. So it's kind of like moving the angle with respect to Y and moving the angle with respect to X to perturb it and get a cool effect like this. Okay, I think that's everything. Thank you for listening. Bye.